Back in 1905, Einstein realised that space and time are not separate, but they're woven together into something that's often called the fabric of the universe, or more technically, space-time. But we now suspect, or at least we have a theory, that space-time emerges from something deeper, which is just basically quantum entanglement. So we think that there...
Essentially what he's saying is there's no such thing as space-time, or they're woven together. Complicated stuff.
It's a description of our universe, which is just bits of information, basically, or qubits to be more technical, quantum bits of information that are entangled together in some sort of network. So space and time don't exist in that network, and then space and time emerge from that deeper theory.
Oh, I see. So space and time come from something else. I think that's what he's trying to say. So, you know, when you think of space and time, maybe a very primitive way of thinking about time. When I think of time, I just think of a clock or a watch. You know, it's 12 o'clock right now, or 6 o'clock in the evening, and you've got 24 hours, and that's time. For me, that's how I see time, that's how I read time, that's how I understand time. You know, 24 hours in a day.
This is cutting-edge physics, but it's one of the pictures that we have for what space and time might be. Europa, Jupiter's moon, is a prime candidate for a habitable world.
Oh, Jupiter's moon, Europa. I definitely know about this one. One of the moons around Jupiter, and it's called Europa. Could possibly be habitual, as in organisms, microorganisms might live on Europa or survive somehow.
In the, what we know, almost certain, I'm always, the people who I know who work on the mission say, don't say we know, we're almost sure there's a saltwater ocean below the surface. I think it's pretty indisputable now, so we're pretty sure it's there.
Yeah, but whatever is the skepticism, what would it be were it not a global ocean?
Yeah, it's very difficult to be, because, and that's from many measures.
When they say ocean, they're implying water, and water is life. Yeah. Chances are there could be living organisms on Europa. It's possible. Yeah. Obviously, no one's been there. We've not had the actual evidence, but you know, where there's water, there's life.
Was it made of ammonia? I mean, there's not, you know, water molecule is not rare.
Yeah. So it looks like salt water.
Yeah, and we have a lot of comparative planetology with, is it the Arctic, when it freezes over, you have these chunks of ice that will break and refreeze and readjust, and you can compare the images and you'd think you were looking at the frozen Arctic.
Yeah, yeah. Quantum mechanics lies at the heart of transistors. Okay. So the phone that people are using to watch the stuff about quantum healing operates on the principles of quantum mechanics. Really? That's how transistors work. And we call this a wave function, and it's something to do with the probability of finding the thing somewhere. But there are different interpretations of that, and we don't fully understand the theory. But it does work, because your phone wouldn't work if we didn't understand it.
Really? No way, man. Your phone's not going to work if we didn't have quantum mechanics, or the theory behind quantum mechanics. That's really interesting. I didn't know that.
Mechanics. And then there's quantum computers, which we're beginning to develop now, which are potentially very powerful things. And there's quantum teleportation, which is teleportation.
Oh, wow, teleportation. I wish I could teleport.
Actually works, you know, with photons that the universe is stretching or shrinking. So the fabric is stretching or shrinking. Either way, if it's stretching, then that implies everything was closer together in the past. If it's always been stretching. Right? So that means everything's close, which looks like an origin to the universe. And if it's shrinking, of course, it looks like there may be an end. That implies maybe an end to the universe.
It's definitely not shrinking, it's definitely expanding. I think I've read that.
So either way, I think Einstein's theory, it's quite difficult to have an eternal universe in Einstein's theory. And he didn't like that, for the reasons I think we're talking about.
I thought Einstein was quite religious, like he was a practicing Jew, so why would he not like that? I don't get that.
If you have an origin, you have to start saying why. What is that thing?
Maybe what Brian is saying is Einstein didn't like the fact that he had to then explain the existence of God. When you say origin, something has to originate from something or somewhere. And how do you explain God? You know,
means have a beginning. It turned out that experimentally, in the 1920s, Edwin Hubble discovered that the universe is expanding. And so that once you've got that measurement...
So about 100 years ago, Edward Hubble, with evidence, proved that the universe is expanding. But like I said before, there are religious texts out there that have explained expansion of the universe centuries ago. It's interesting.
And again, I talk about this in the show. We have those measurements now for thousands and thousands and thousands of galaxies. So we have this whole map of how the universe has changed and evolved over time, experimentally. And then with Einstein's theory, you can figure out when everything was on top of each other, which is 13.8 billion years ago.
Oh, so is he saying the universe is 13 million years old? So what he's saying? Let me know in the comments.
I have this question of an origin, but just to say, it's not being uncomfortable. It goes back to what you said about being terrified. It's not unnatural to worry about that, what it means to have an origin to the universe, because Einstein didn't like it, right? He was worried about it, although he accepted it ultimately because that's what the evidence tells you. Now, I should say,
why would you worry about it?
Now, we still don't know what it means, that an origin. An origin in time, was it really the beginning of time? Stephen Hawking and many others have thought about these no boundaries things and all sorts of things where you don't really have an origin in time. We don't actually know what time is.
What? We don't know what time is? I guess, you can measure time, but okay, I agree. We can't explain what time is. We can measure time based on movement of the planets. Moon, for example, 24-hour day. But how do you explain time? Maybe it's quite philosophical at this stage.
I tend to say that we don't know. Space-time, we talked about before, may well come from something else, which is deeper. We don't have the deeper theory yet. We have ideas, it's called quantum gravity. Until we have those deeper theories, then we really talking about the origin of the universe is very difficult. For example, there's something called the inflationary multiverse.
He's explaining multiverse or multi-universe. Multiverse, many parallel universes.
To be the way that it is.
If you haven't seen Doctor Strange, watch it. That's a good explainer for multiverse.
Is that before the Big Bang, then space and time still existed, and space was stretching very fast. It's a theory called inflation. And then that period of time draws to a close, so that the expansion rate, this incredibly fast expansion rate, slows down, and kind of the energy driving it collapses, changes form or state, and that's what we call the Big Bang. So the Big Bang is the end of inflation. Extensions of that, called eternal inflation, say or suggest that maybe that collapse at the end of inflation, maybe it doesn't all stop at once. So you're to picture patches of this rapidly expanding space that are sort of collapsing and making big bangs, which make universes. And so that the process is called eternal inflation, because for all we know, it could have been going on forever in a sense, and would be going on now, if that was correct.
So what, new planets, new universes? Okay.
So we would just be a bubble in this sea, an infinite sea of universes, of which we're a single bubble, and that's called the inflationary multiverse. Quantum mechanics does appear to suggest that really there are an infinite number of universes. So every possibility for every interaction that happens has a probability of, it's like rolling a dice, and you could say, well, I roll a dice and it comes up a 3, but it could also be a 2 or a 4. And basically, the many worlds interpretation of quantum mechanics is that there's a universe in which every dice roll happens. So you get an infinite number of copies of you, for example, in this inflationary multiverse. Not the inflation, the many worlds interpretation of quantum mechanics. Consciousness is, I think, and it's becoming very...
Okay, so he's saying we potentially could have multiple universes where your copy, your own self, is mirrored in that other universe. I guess there's no evidence for it, but it's still a theory, right? So
Topical, because of course AI and the potential development of artificial general intelligence, we're not there yet, but AGI, raises this question of what intelligence, what the experience of being human is. And so there are different, I think there are two categories of emergence people speak of. Actually, Sean Carroll, if you had him on the show, he's got about 5 in a recent paper. He's got loads of category 2A and 3B or whatever.
Okay.
But broadly speaking, people think of weak and strong emergence.
Okay.
So weak emergence is what I think virtually every scientist would, certainly a physicist would say consciousness is, which is very complicated, the most complicated emergent phenomena we know of in the universe, I would say. But it comes from the underlying laws. So you could model it with a sufficiently powerful computer. You could imagine modeling how the human brain.
I don't know. I think that's quite far off, to be honest. Yeah. We see it in films where AI has sort of taken over the world and it thinks like a human brain. It's science fiction at the moment, but could happen potentially.
I think most people would accept. There is also strong emergence, which is somehow the phenomena you see is not, you can't simulate it from the underlying laws. There's something else going on. Now, I would not subscribe to that. So I would say consciousness is interesting because it's weakly emergent. It emerges from this thing, the brain. How, we don't know. So you have Kepler, Galileo. It's shortly after Copernicus, just before Newton, decades before Newton. And so that is the moment, really. And it is almost a moment. Many historians would agree. There's obviously things happened before, but it's the time when we started saying we can look at nature. So Kepler was interested in the motion of the planets in the sky, and he figured out around 1610 that the planets move in ellipses around the sun from the data that had been acquired. So it's the time when we start using data to...
You would think the planets go around the sun in a circular orbit, right? That's what I thought, but that's not the case. It's a different shape.
Old models of the world, that didn't really happen before around 1600. Not in that way, and certainly not in the way that Newton did it in 1687. So that idea that you start out, doesn't matter what you think. I mean, Kepler had all sorts of strange ideas about platonic solids and all these things, and which were really based on Greek ideas. And the cosmology at the time was Aristotle's cosmology, that the Earth is motionless at the center of a finite universe. That all went in a few decades, around 1600, because of observations of nature. So that's a big change. And many historians argue that that's the beginning of the modern world in many circumstances. So we're just sitting here now, the Artemis 2 spacecraft has just gone around the moon and landed back on Earth. Yeah. That trajectory, which is quite remarkable if you look at it, the way that the moon, have you seen those graphics online where the moon's coming and the spacecraft goes around and comes back, and it landed within about a mile, I think, of where it was supposed to land.
Wow, the maths today, man, it's so damn accurate, Wow.
Pacific Ocean. That's Newton's laws that are used to do that. Yeah. You don't need relativity. So you don't need the more complex model. And so we discover those. That we've not discovered anything smaller than that, by the way.
Is it because you don't have enough energy to bust up a quark?
Yes. Or to resolve what's inside it, let's say, to build a microscope.
Because right now, the inventory of fundamental particles includes quarks. Yeah. So somebody saying that's fundamental, which sounds a little like the Greeks saying atoms are fundamental.
Oh no, well, they won't be fundamental. You're absolutely right. But they look point-like from the point of view from the energies that we can generate today. But that's one side of particle physics. So we've been exploring the structure of matter. When you think about what a collision is, so let's say you collide, as we did in my PhD, electrons and protons together. So you get an electron beam and a proton beam, and you smash them into each other. What's actually happening? What's actually happening is one way that the collision can happen.
Isn't that how they make bombs, like the atom bomb and all these bombs? They sort of collide different particles. I think that's the theory, isn't it, behind atom bombs?
The electron can emit a photon, which is a particle of light. And the particle of light goes and it hits the proton. Now, the wavelength of that light which is telling you how small a thing you can see, is proportional to the energy of the thing. That's how hard we're smashing the things together. So the faster you smash them together, so the faster you smash them together, the higher the energy, the smaller the wavelength, so the smaller the things that you can see. So that's a way of thinking about particle collisions. So it really is a microscope in that sense. Okay. That analogy works. What it means to have an origin to the universe. Because Einstein didn't like it, right? He was worried about it, although he accepted it ultimately because that's what the evidence tells you. Now, I should say, now that we still don't know what it means, that an origin. Mm-hmm. An origin in time, was it really the beginning of time? Stephen Hawking and many others have thought about these no boundaries things and all sorts of things where you don't really have an origin in time. We don't actually know what time is. I tend to say that we don't know space-time. We talked about it before. May well come from something else, which is deeper. We don't have the deeper theory yet. We have ideas, it's called quantum gravity. Until we have those deeper theories, then we really talking about the origin of the universe is very difficult. So it's fascinating and it's current research. So I say in the show, and I say at the end of the show, and it maybe if there's one moral to my live show, it's that we don't know is the most powerful phrase.
Wow, we don't know. He's so right, man. There's so many things we don't know.
Language, because what it means if you say we don't know is there's new knowledge to be gained.
Wow, that's something brilliant what he just said. If you say we don't know, that means it pushes you to investigate, to do the research and find out the answers. That's how we progress, right? Imagine 100 years ago, we didn't have planes. 20 years ago, we didn't have mobile phones.
And if you don't accept that there's new knowledge to be gained, there is no progress. So progress, our civilization rests on people realizing that we do not know everything. Right? It's the most important thing. And it's also very difficult for people. You see it everywhere, right? People don't like to say, I don't know. But there's no science without that. And he said it's not even imagine, it's guess. I remember Feynman saying in a lecture. Yeah. He said, we guess. Don't laugh. And everyone laughs. And he goes, don't laugh.
So do you guess?
But we guess. Yeah, that's what theoretical physics is, right? You guess. He just said, don't make it.
Yeah, I guess imagine is the wrong word. You would guess, right? You could guess option A, B, or theory A, B, and then you work on those. And
well, you guess about it. Obviously, it's an educated guess, but you make a theory, which is a guess. And then you see what the theory predicts, and then you have to go and test it. And as Feynman very famously said, if your prediction disagrees with experiment, it is wrong, and it doesn't matter who you are, or how famous you are, or how many titles you have. If your theory disagrees with experiment, it is wrong. And that's it.
That's brilliant what he just said. Do you agree?
That's it, that's all. Actually, in the show, so my live show, it starts with Johannes Kepler, on the Charles Bridge in Prague, 1609, as Kepler wrote. New Year's Eve, 1609, he was walking across the Charles Bridge to a party, and he was looking at the snowflakes landing on his arm, and asking questions about the snowflakes. Why they're the shape that they are, why they have 6 corners. And he wrote a beautiful book, which you can still get, called The 6-Cornered Snowflake.
Maybe we should all get that book and read it. Well, that was interesting. It's an eye-opener. Certainly for me it is. What do you guys think? Let me know in the comments. I think I'll just continue to make such videos, sort of react to them. Or for me, science and science fiction and universe, these are interesting topics. Let me know in the comments what your thoughts are. See you later.